Hi, everybody. My name is Gordon Long. I'm going to be talking to you today about who guards the guards, hiding your C2 comms in plain sight. I even have a fancy little Latin quote here, which essentially just means who guards the guards themselves. Before I begin, I just want to give a big shout out to ZeefCon. This is actually my first time here, and it's been a great experience so far. Thank you so much for inviting me to speak. It's been a really fun time. So let's get into it. So who am I? Like I said, my name is Gordon. I'm from the US. I'm president and founder of LegUX Cyber Technologies, which is my own little security startup. I'm also a senior offensive security engineer at Zoom. What that essentially means is I'm a red teamer. I also am an adjunct professor at George Mason University, dabble in their Masters of Computer Forensics program. And just to get the legalese out of the way at the beginning of the talk, my views are my own and do not represent any of the aforementioned companies or institutions. So, I'm not going to go over this entire outline right now. You can reference it later, but the one big thing I did want to say here, because I realize the talk title can be deceptive. All right, no laser, that's fine. We're going to be talking about C2 modular communications today, not like hiding your C2 network comms. So I understand the title might be a little confusing there, so just want to point that out at the beginning. So, to begin with, we're dealing with Windows in this talk. We're going to be talking about what the state of EDR on Windows is today, what we have to deal with as attackers, okay? Most people here, I'm assuming, are familiar with the term EDR. I'm not going to go into the MDR, XDR, way too many acronyms for this industry. But if you're not familiar, just think of it as tools that live on endpoints that can do a lot of different things. They can do detections, they can do actual active response, they can also just do logging, telemetry, etc. But on Windows specifically, EDR tends to use one of two approaches. So it either uses userland hooks or kernel-based hooks, or sometimes both. Today, just based on my own experience, what I'm seeing in the industry, a lot of the more advanced EDRs are starting to switch more into kernel-based detections. There's been a lot of activity around userland unhooking and other techniques in userland that attackers can use to try and make telemetry less reliable for EDRs. So there's been a bit of a push to have a lot more of your telemetry coming from kernel, which kind of ups the game for attackers in terms of if you want to disrupt that telemetry. So as attackers, we kind of need to be expecting to go up against kernel-level defenses these days. So based on that, we have some choices. We know we have to deal with the kernel, so we can either choose to go into the kernel ourselves. That means trying to load vulnerable drivers, trying to mess with kernel memory, trying to prevent telemetry from going to the agent, maybe doing unhooking inside of kernel memory space. You can also try and go above or below, so get yourself loaded at the hardware level, get yourself loaded before the EDR even is loaded, or try and do things on the network, try and prevent telemetry from going out across the wire to inform people what's going on. We're not going to deal with any of those methods today. We're actually going to stick just to userland. And so if you're in userland on Windows and you know you have to go up against the kernel, what that essentially means is you're going to be seen. You're going to be looked at. What you're doing is going to be looked at. So you need to act accordingly. Everything you do will be watched. So how do you still try to blend in? How do you still try to evade EDR? So I love this picture. This is really my only meme slide in this talk, but I love this picture because it does pretty much describe what we're trying to do. You want to blend in as much as possible with the stuffed animals being a cat. One of the ways that you can do that is by staying as still as possible, as you can see in this photo. So the analogy there is we're staying as still as possible. What that really means is do the least amount of bad that you need to accomplish your goals or objectives, right? A lot of times when people think of red teaming or pen testing stuff, they think like, oh, I'm going up against Active Directory, I'm going to grab that domain controller, but do you actually need to do what it is you're looking to do right now? What is the minimum you actually need to do to accomplish your objectives? So always keep that in mind, especially when you're in userland. And I recommend utilizing a stage 0. What I mean by stage 0, just a simple loader. Most of the functionality in this loader, especially pretty much all the functionality that's going to be on disk, is going to be benign. You're not going to do anything crazy here. You're going to have basic reconnaissance capabilities. You're going to be able to look at basic system information. You might want to confirm that you're on a target that's in scope, for example, before you do anything else. But you're going to have some kind of loading capability as well. So anything that you need to do that's a little crazier, anything that's a little more advanced, you're going to load that in as post-exploitation modules. So keep yourself as benign as possible on disk, have a loading capability, and there's multiple reasons to do it this way. This actually isn't even true just on Windows. This is a good rule of thumb across the board. If you keep yourself tiny and small and don't really do that much, it's actually pretty easy to write to. So if you get burned, it's easy to write a new one. And if you get burned, there's not necessarily a whole lot that can go into reverse engineering it. There's not that much that lives on disk. Okay, so we're going to briefly touch on named pipes in Windows. I'm sure many of you are familiar. Named pipes are used for communication between processes and objects over network and locally on Windows. They have a server and a client component, which means essentially that multiple clients can talk to a single server instance, which makes them useful for communications. And they utilize SMB remotely or RPC locally. The reason I'm mentioning named pipes at all is because a lot of C2s like to use them. There was actually a talk yesterday that was talking about ways you could try to detect named pipe creation for this exact reason. I'm sure some of you have heard of Cobalt Strike. Cobalt Strike loves to use named pipes. It's all over its documentation. They have a lot of built-in ways that you can try and change around what the defaults are that are set in regards to named pipe names and arguments. Stuff like that, but it's used for post-exploitation, for staging, for communications, for payloads, so it's used all over the place, not just by Cobalt Strike, but by many C2 frameworks. So yesterday this was touched on as well, but there's been a lot of research from the defensive side in trying to hunt based on named pipes because they're used all over the place. There's actually a lot of legitimate usage as well, which is part of the reason why C2s have defaulted to using them. I show you just a small snippet here. Hopefully this is visible. I've learned don't use dark backgrounds for slides. But there's 87 named pipes running on this little Windows VM that is running nothing malicious. It's actually just running Firefox and Mozilla. And you can see there's already just tons and tons of named pipes all over the place. So a bit of a pain. If you are trying to hunt for them, there was, again, talk yesterday which talked about different ways to try and hunt on them. But there's been a bunch of blog posts on ways trying to hunt just by name. If people are lazy, again, there's defaults used by a lot of these C2s. If you don't change some things around, it's pretty easy to catch you. If you do try and change things around, it becomes a little bit more of a pain. But I just wanted to say EDR is starting to focus much more on this topic. Defensive products are trying to focus much more on named pipes. So that was leading me down the ideas of, all right, do I need to use named pipes at all? Can I try and achieve some of the same objectives without utilizing these structures? Because they're starting to be scrutinized significantly more. So my idea was, okay, I don't want to use named pipes. What else can I use instead? Why don't I just look at trying to use my own process memory, or just memory in general? So we're going to talk just briefly about how EDR might try to hunt you in memory, and what some of the things that you might want to try to avoid as an attacker. So just basic stuff. The EDR is going to look for permission changes and just permissions in general. So if you have a region of memory, this is very well known, that's read-write executable. Why is that? That's kind of weird, unless you're in a .NET process, but that's a story for another day. I don't know why they use so much read-write execute memory, but they do. But you want to avoid doing that if you don't need to. You also need to be careful if you're going to be invoking the Windows 32 APIs or system-level calls that deal with changing memory permissions. If you do these things in too quick of a succession, if you do certain calls back-to-back, that's also very suspicious. So the classic example is using virtual alloc. You allocate a read-write page in memory, you write to it, and then you change that permission to read-execute. That's a classic sign of injection and malware trying to execute its code. So there's always a cat and mouse game. You insert delays, you do other API calls in between, but those are things you have to watch out for as well. EDR is also going to look at whether memory is backed on disk, so whether it's tied back to something that's on disk, a DLL, etc. This is very well known. There's lots of techniques that talk about trying to get around this problem. module stomping, there's a ton of them, so won't go into too many today, but just something else you have to be aware of. And again, EDR is trying to look at code execution. Where are your threads coming from? Are they tied to things on disk? What is it you're trying to execute? That kind of thing. And then, as other talks have pointed out, they're looking for entropy and actually even static bytes. So you'll have scans in memory that look for specific static bytes. These are often tied to things like Cobalt Strike. If you don't do any changes, you're going to get caught very quickly because a lot of these bytes are signatured. And if you try and use too much encryption, et cetera, that entropy can also get you caught because it's weird to have too much randomness. This is why attackers like to use things like encrypted sleeps. I highly recommend, I hope you got to check out the talk yesterday, but if not, check out the recordings because that talk yesterday that also talked about dealing with named pipes also mentioned ways in which you could try to catch encrypted sleeps based on timers. So, basic Windows memory permissions. I'm sure many of you are familiar with these pages if you've done any Windows dev. But we've got the basic page execute, read write, stuff that I mentioned before, page read only in the left box here. But we're going to be focusing more on the right box today, and that's specifically modifiers, essentially, that you can add to these regions. In particular, we're going to be talking about the page guard permission. Page guards aren't new. They were originally designed to help prevent stack corruption. So there would be this region of memory that was allocated at the end of the stack that if you overwrote your stack too much, you would hit this memory region, and you would hit the guard page, and the guard page would trigger an exception. Now, normally this exception is handled by the system. If it notices that it's the thread that is tied to that stack, it will automatically add more memory for you, set a new page guard permission at the top of the stack again, and just do dynamic memory allocation. So this is preventing stack overwriting and stack corruption. So notice exceptions will be triggered. This is interesting. I'm not the first person that's thought of utilizing guard pages for badness based on these exceptions, and we're going to go into some of the history of them in a second. But I did want to point out, hopefully it's visible here, notice that all of these page guard regions of memory are tied to specific stack threads, or thread stacks, I should say, specific threads. And you can see those thread IDs there. This is just a basic system informer view. If you open up any process on a Windows box, pretty much all of them will contain these page guard regions because they are tied to legitimate threads. So, like I said, I'm not the first person that's thought about, oh, these page guard regions, they're interesting. So one of the previous uses for malware for guard pages is you can actually use it to try and detect if you're running in a debugger. So basically, you could set a page guard region of memory, purposely try to access it to trigger the exception. And if you don't see this status guard page violation, you know you're actually running in a debugger. If you do see the exception, you're not running in a debugger. Debuggers also utilize guard pages for doing things like breakpoints. And this is actually covered. I wanted to give a shout out to Sector 7. I know they're sponsoring this conference. They talk about this in their Malware Development Advanced course. They're also going to talk about the next thing that we're about to touch on. But definitely check that out if you want to learn more about some of these techniques. So the other big thing, and this was popular for a while, pretty clever method, came out over a decade ago now, is implementing these guard hooks and these vectored exception handling hooks, essentially. So vectored exception handling are basically customized exception functions that you can implement inside of your code so that if an exception happens, it does what you want it to do instead of the normal system handling of exceptions. So you could use this along with guard pages. You know you're going to trigger exceptions. You could use this essentially to trigger your own custom functionality, right? So you could do things like building encrypted sleeps by if you have a region in memory that is triggered by like an EDR scanning memory, for example, it will trigger your guard page, which will trigger an exception, which then forks over to your exception handler, which can suspend your thread, change the permissions in memory. We'll go over a basic example in a minute. But is a nice way that you can try and react to things happening on the system in a way that you can control. You can also use this technique defensively. There was an interesting blog that I read of EDRs trying to utilize a similar-ish kind of technique where they would add in fake DLLs that were loaded into process memory. And so if attackers were trying to crawl and get to, say, like NTDLL, the module NTDLL, they might hit a fake NTDLL, which is going to have guard pages in it. And while they're trying to crawl that DLL looking for what have you, they're going to trigger the exception and actually cause the EDR's vectored exception handler to activate, do certain things, look more at what's happening. So you could use it actually both ways. There's a bunch of examples of this. Like I said, it's been around for over a decade. It got really popular because you didn't have to modify bytes in your process memory to install hooks. This is why people liked it. Also covered in that Sector 7 course. So again, check it out. But we're going to go over this medium example here just to show you what that kind of looks like. So this is some basic code that would install a hook. You can see the handler function at the top. That's going to be looking for that status guard page violation. If it notices that guard page violation, it's going to redirect execution to a customized function called myCreateProcessInternal. And what they did is they actually set the first page on the normal Windows 32 API create process internal to a guard page. And so as soon as EDR tries to call that function for memory scanning, it would trigger their exception. They'd redirect execution to that myCreateProcessInternal, which would do what I was talking about before of suspending the main malicious thread, setting permissions to page no access so EDR couldn't scan it properly, waiting a certain amount of time before setting it all back. So just a very basic example of the APIs you can use. It's that add vectored exception handler is the API to add in your own customized exception function. And that's located at this Medium article here. And notice the virtual protect call, that's how you can change memory permissions to add in your page guard. It's just that little modifier at the end. So obviously this was pretty popular for a while. Of course, when things get popular, the defensive industry tends to notice and start to look for it. So defense started taking some stabs a while back, several years ago. And you actually, it turns out, can tell whether processes are using these vectored exception handlers by crawling the PEB and looking for a specific bit. And you can actually see the structure here in memory that you would look at. Essentially, you're just looking for process using VEH. That's that vectored exception handler. You would have the same for that process using VCH. VCH stands for vectored continue handlers. I do want to point out, it looks like there might be some room to play with vectored continue handlers. There's not a lot of research done on them, using them for offensive purposes, but they also can act based on how exceptions are handled. There's a certain load order for when they get called, so might be interesting to play with those as well, but you can actually detect both of them being used in processes in the same way. The VEH and VCH structure is a doubly linked list, and so you can crawl those lists to see what modules those customized exception functions are pointing at, see if something weird is going on. So that's how EDR often tries to hunt for these today. You can check out this article at the bottom if you want to read more about that. So that's just kind of covering the history of malware using guard pages, abusing these exceptions. However, I had a different idea. I was like, okay, these are all very interesting methods. I like these customized exception handlers, etc., but they're pretty loud these days. What if we try to utilize guard pages instead for code execution? What if we just use these for data storage? So remember, I was talking about trying to avoid using named pipes. Well, what if we just design our C2, our stage 0, to load in a module, and when that module fetches data, we'll have the module actually allocate to a region of memory and then set permissions for guard pages. There's some advantages to this. We don't have to deal at all with executable bits of memory, which makes memory a lot less suspicious to EDRs. And we get to avoid named pipes, as I said. If EDR tries to scan too much with guard pages, it's a little bit of extra overhead, but also EDR needs to be very, very careful, because as I mentioned before, page guards were introduced legitimately to try and prevent stack corruption, right? So if you scan a region of memory that is page guard protected and you don't take subsequent action, you'll actually remove the page guard permission by default. That's how it gets handled, and you risk corrupting the stack and crashing processes. So you'd have to be careful when trying to scan memory and dealing with page guard permissions. And then you can actually, if you're being scanned, we'll talk about ways in which you could actually use that to your advantage to detect that EDR is looking at you based on these page guard permissions and takes action accordingly without utilizing those vectored exception handlers we were just talking about. So what we're going to do, we're going to design our post-exploitation modules to grab some data, whatever it is that you want to do. This is a pretty general approach. Then you're going to allocate your region of memory. You're going to set it to read-write. You're going to stuff the data in there. Then you're going to add the guard page bit. On top of your regular data, you're also going to add in a particular header and footer. And then your main stage 0 can crawl your own process memory space and look for these page guard permissions. It knows to look at the page guard protected pages. It will change those permissions to read-write. It will check for the header. If it doesn't find it, just change it back. If it does find it, it knows it's found your data. So this is just the basic example of how you could set up a DLL with an exported function. To do this, you would insert whatever functionality you want here. In this case, I'm just doing a get process list. You add your header bytes to the front of that data set, add your footer bytes to the end. You allocate just a basic region in memory. Don't worry too much about the sizing stuff. The times 2 is just because I'm using wchars instead of regular chars. But you'll write your data in, and then you'll set that protection to page guard. And then your main stage 0 will have, you could do this in different ways, but this is just the dumb example. You'll have your header hard-coded in that stage 0. It will crawl your memory process space and look for the page guard permissions. And then if it actually finds the header in the region of memory, it knows it's grabbed the correct data. I did want to point out here, I have virtual query X as the Win32 API that I'm using. I left that in because you could do this with remote processes as well. It doesn't need to be local process, but I would personally recommend you stick to local process if you can. It just tends to be a little bit less loud, a little stealthier for EDRs. They tend to care less what you're doing in your own process memory space, as opposed to if you're interacting with other processes in memory space. So I left your virtual query X in to just say you could do this with remote processes, but I wouldn't necessarily recommend it. So use virtual query instead if you're just going to do your local process memory space. We're going to have this buffer here that we're reading into, this info buffer, and we're going to talk about some of the limitations of this in a second. But once you read in, like I said, compare against the header. If you find the header, you know you got your data, you can print it out, you can send it somewhere, do whatever it is you want to do, and then you're actually going to reset the region to 0. You're going to just set zeros there, just clear it all out, and then you can just free that region of memory, and you're good to go. If you don't find the header, just, again, set the permissions back to what they were so you don't cause any stack corruption. Don't want to crash the process. So let's do the first demo. So don't judge me. I did the very, very basic and not OPSEC safe, just load library and get proc address and stuff like that. This is just to demonstrate the technique. This is not to show you the best and best ways to use it. But what we're going to do is load our process listing DLL. This would be our post-exploitation module. We're going to find the exported function address in memory and then run it with create thread. We're going to look at our process memory space here, and we'll notice we've got a few, hopefully you guys can see this. We've loaded our process list DLL. And then as we continue on, and there's our exported function. As we continue on, I just wanted to show you it's a basic DLL, nothing crazy here. You'll notice we actually already have a bunch of read-write plus page guard regions of memory. There were 4 of them there. Like I said, all processes are going to have them legitimately. We're just going to jump ahead, do our create thread. Our post-exploitation module should be finished now. So if we refresh our memory in our process, we're going to see a new region. That's read-write plus page guard. That's 24 kilobytes. Notice, however, it's not tied to any particular thread stack. And we're going to talk about that in a minute. And how it's a bit larger. But that is our region in memory. That's actually where our data is located right now. And our stage 0 can find that as we continue on. Going to look for that header. We find the header. We print out the data in just a second. And it also shows you all the other page guard regions it found in memory. That's obviously for debugging. Don't do that in your actual stage 0, printing that stuff out. And we'll notice if we refresh again, that page guard permission is gone now because our stage 0 has reset the permissions just to read-write, so it can read the data. And there's all the process listing data, including our header and footer in there right now. So we'll just print that out. And we've grabbed our data. Once we're finished, we set that data, that region to all zeros, and we free that memory. and we're good. And you can see all the information that we fetched. Again, basic example of just a process list. But you can insert whatever kind of post-exploitation module that's going to gather data for you here. All right. Let's see if we can go back. Yeah, perfect. So definitely some disadvantages with this method. We have a lot of size constraints. If we're reading into that smaller buffer, if you're expecting to get like 2 gigs of data back, I would not recommend using this approach. You could use heap memory instead. I encourage you to play around with it, but there's a little bit more work to control it. And just the way that the heap allocates into memory itself, you have a little bit more things to worry about. As I pointed out, there was no tie to an existing thread stack. And that's kind of a problem. Kind of sticks out. Kind of weird. You could utilize userland unhooking. I'm just using the regular Win32 API for the demo. There is actually a debate here of whether it's smarter to do that or not, because a lot of EDRs aren't doing userland hooks anymore. Sometimes it can actually look weirder to try and do direct system calls as opposed to just using the Win32 API. So there actually is room for debate there. And then consider the sizing of the data itself. Remember, we allocated this new region of memory, this new read-write plus page guard, that was 24 kilobytes. And if you noticed, all the other regions of page guard memory were just 12 kilobytes. So we're already double in size of what a normal region looks like, which is not great. Maybe if it's just 24, you'll get away with it. But if you're allocating 500 kilobytes of memory, et cetera, that's going to look really weird compared to a normal read-write plus guard page section. Again, recommend doing this still mostly locally in your own local process. You could do it remotely, but and then we also didn't do things like encrypting the data before we stuffed it in the memory region. There's other ways to play here. You can do more dynamic headers and footers versus the hard coding. Just wanted to show you the basic example. I did want to make this approach as general as possible, and you can integrate this with your own custom C2 tooling for sure, but based on this approach, unfortunately right now, you would still need to rewrite your stage 0 at least a little bit, and your post-exploitation modules, you'd at least need to wrap them in a way that your modules know to allocate their data in this way, and your C2 knows to fetch it this way. So definitely a general approach. You can integrate with a lot of tooling, but it is going to take some work and some rewriting to do. So like I said, if we want to detect this, you can look for that non-backed memory. You can look for the weird region sizes compared to normal page guard memory. And then you would look in kernel for the memory calls based on virtual protect. Why are you virtual protecting with guard page memory, setting it to read write, and sending it back to guard page, and you're doing that continuously in a very short span of time? Kind of looks weird. You could add in some delays, et cetera, as an attacker to try and mitigate some of that, but if you do focus in on those, it might be a way you can detect this technique. And especially, why is this happening all over your process memory space in a very short span of time? So to fix some of these issues, I call this first method that I just demoed for you guard comms. This second method I'm calling guard stomping. So instead of having our post-exploitation modules allocate a new region in memory and set it to page guard, we're going to abuse those existing guard pages that are in pretty much every process. So instead of allocating new regions, we're going to write over data inside of these existing regions. So that's not going to be a lot of changes in your main stage 0 here. Instead of freeing the memory when you're finished, you're just going to set it back to zeros and then virtual protect it back to page guard. If you don't find it, the exact same as before, just set it back to page guard. Ironically, based on my research, page guard pages normally are filled with zeros anyway, which makes your life pretty easy because you don't need to try to remember what data was there before to restore it. You can just set it back to zeros, and that's exactly what it looked like before. Our post-exploitation module, we're going to have to do a little bit of work on. So now you're going to have to add in querying for your own process memory space or remote process memory space, looking for those regions in memory, so then you can do the set this to read write, write to it, set the permissions back, etc. And so there's a bit of complex math here again because I was using wchars, and I did want to point out, if the laser works, oh, there it is. This is a little bit of a typo here. This should have a divide by 2. It's going to be corrected in the code that I publish after the conference is over. But just wanted to point out that this actually should have a divide by 2. But this would also be a lot simpler, and you wouldn't have to be worried about these divide by 2s times 2s if you're just using regular chars. So really up to you. Do the second demo. So this is just going to demonstrate guard stomping. We're going to jump right into the post-exploitation module. We're going to use virtual protect on the regions of memory that we catch. And something really weird is going to happen. And I actually still don't know why this is. So if anyone in the audience has an idea, I would love to hear it. Something odd occurs when we use virtual protect on this first region of PageGuard memory, or really any region of PageGuard memory that we find. And that oddness is going to be the size changes dramatically of the region. I still don't know why this is. This is also true if you try to use NT protect virtual memory. It doesn't matter. The same thing happens. So if we actually jump up to that region, it now no longer has the PageGuard, but it's also now 520 kilobytes in size. And you'll see the first 12 kilobytes are still the zeros like they were before. We haven't even added data to this yet, but then there's just a bunch of random bytes written there. Again, no idea why this is. Didn't have enough time to play with it before the talk. But once we write our data, it stays the same size, but you can see we still only wrote like the 12 kilobytes of size. And then there's a bunch of random bytes. As soon as we protect it and add in the guard page bit again, it goes back to 12 kilobytes. I have no idea why it is. It's very weird. I hope somebody in the audience has an idea. But just one of those things that's definitely made me scratch my head. I just added in some more debugging here. So you have to be careful, and you have to only write as many bytes as you have space for, including your headers and footers. So you're much more limited on how many bytes you can write per region. Like I said, that's usually around 12 kilobytes. Not a ton of size, so sizing does remain an issue. But we've written our data into existing PageGuard memory. You can see it's still tied to those thread stacks, blends in a lot better. And then we'll go back to our main stage 0, which will query through our memory, looking for those permissions. And once we find that information, we print it out. And then before we quit, I'll just show you if we look at those regions of memory again now, we'll refresh. We have our data. They're just going to be filled with zeros. It's going to look totally legitimate, just like it did before. So we're still tied to thread stacks. If we change that permission manually just to examine what's there, it's just going to be all zeros, which is exactly what it would have looked like before. And that's for each of the regions that we wrote to. And that is pretty much the end of that demo. And so just wrapping up here quickly. You can jump back to the presentation, I think. Yeah, you can jump back. So just wrapping up really quickly. Benefits of using guard stomping. Obviously, we're now tied to normal threat stacks. A little bit more annoying for EDR to find us. We're using the normal sizes of guard pages, so that's another indicator that's gone. And again, guard pages are normally filled with zeros, so that's great. However, you still have some problems. There's still a lot of sizing issues. There's ways that you could try to tackle this. You don't even know necessarily how many PageGuard regions there will be. You could try to do things like introducing benign threads that are always going to have their own PageGuards and adding more and more to build more space, but you can only go by about 12 kilobyte increments. So still, if you're expecting 2 gigs of data back, not the best way to go. You could actually try to combine some of the older methods with guard stomping as well. I wanted to hint on this, and we'll talk about this again in a second, but instead of just stuffing data here, you could try and do things like stuffing shellcode here and dividing it among different regions of PageGuard memory that's already tied to different thread stacks. But you need to be very careful because these PageGuards exist for a reason when you remove them, and if you're running code, you always run the risk of corrupting the stack and crashing your process. Might be better to do that if you know exactly what the thread is going to do and you control it. You can make sure it's not going to try and allocate more memory randomly or overwrite its stack memory space. And I recommend, just as other usages for this, you can play with guard pages to try to deceive the EDR. So we talked about before how EDR, it's kind of painful if it wants to be scanning your memory and dealing with guard pages. Well, we can actually utilize the fact that if you try and touch a guard page region and you're not tied to the thread stack, it just removes the guard page permission. We can constantly query our memory space. And if you notice a page of memory you've set that has the page guard permission, even for a second, if that guard permission doesn't exist anymore, you know someone's tried to look at it and you can take actions accordingly. You don't need to use vectored exception handling. It's less reliable. It's more of a race condition as opposed to vectored exception handling, but it's still a method that you can use, and I think it would be a lot more annoying to detect for EDR because all you're doing is querying your own memory space, and that's perfectly benign behavior. And so you can combine some of these other methods that I talked about historically. You can combine this with guard stumping. You could still use stuff like VEH. I still think there's room to play with VCH. But just wanted to point out, these are not mutually exclusive techniques. These are general techniques that you can mix and match as you want, depending on your needs, etc. And just useful resources and links. There's a bunch of them to learn about historical uses, as well as just ways that you can abuse PageGuard. And that's pretty much it for me. I'm going to publish the code to GitHub here if you want to follow along. I also forgot to add my Twitter handle, but it's @ethicalhacks with an X if you want to add me and talk about this later. But yeah, expect this in the next couple weeks. I'll publish this code for both just basic guard comms as well as guard stomping. And that's it. Thanks for coming to my TED Talk. I appreciate it.